Hello my friends, and welcome back to the You Can Do TV channel. The construction of the multi-purpose amphibious vessel FPSO represents a milestone in Peru's modern naval shipbuilding capability, combining international design expertise with domestic industrial execution at the Sima shipyard. Designed as a landing platform dock (LPD), based on the Makassar-class concept, the vessel was engineered to support amphibious operations, humanitarian missions, logistics transport, and disaster response across coastal and riverine environments. Fabrication began with large-scale steel cutting and modular block construction, allowing multiple hull sections to be assembled simultaneously before integration inside the dry dock. This modular methodology accelerated schedule efficiency while improving dimensional accuracy during alignment of structural frames, bulkheads, and deck levels. Once the keel was laid in 2013, progressive hull erection continued through heavy lift crane operations, followed by installation of propulsion foundations, piping networks, and electrical trunking routes embedded within the structure. As the hull reached structural completion, outfitting phases intensified. Engineers installed diesel propulsion systems, auxiliary machinery, cargo handling equipment, and command and control infrastructure. The ship's internal configuration included troop accommodations, vehicle decks capable of transporting armored units, and a well deck designed to launch landing craft for amphibious deployment. Aviation capabilities were incorporated through the construction of a reinforced flight deck and hangar facilities supporting naval helicopters. Launching in 2017 marked a pivotal transition from construction to systems integration. After flotation, quayside outfitting continued with radar, navigation electronics, communication arrays, and defensive weapon systems. Harbor acceptance tests validated mechanical and electrical performance before comprehensive sea trials evaluated maneuverability, endurance, and operational readiness under real maritime conditions. The project demonstrated how technology transfer partnerships and local engineering capacity can converge to produce complex military vessels domestically, strengthening both national defense infrastructure and industrial expertise for future maritime programs. Steel plates, sparks, and towering cranes set the stage for a vessel built to command power far beyond its size. The construction of the Ocean Pierre Julien, a modern 25-meter tug, represents a highly coordinated marine engineering effort carried out at the Ocean Industry Shipyard on Îlot Coudres. The project integrates advanced naval architecture, precision steel fabrication, and modular assembly techniques typical of contemporary tugboat manufacturing. Initial phases involve digital modeling and structural planning, where hull geometry, propulsion alignment, and stability calculations are finalized. Steel plate preparation follows, including cutting machine, edge beveling, and pre-assembly of hull sections. These components are welded into sub-blocks using controlled heat input procedures to maintain dimensional accuracy and minimize distortion. Once major hull modules are completed, heavy lifting equipment positions them onto the slipway for full hull integration. The defining milestone arrives when the completed vessel is launched and guided into open water for operational validation. Sea trials evaluate maneuverability, acceleration response, braking performance, and towing capability under real maritime conditions. The Ocean Pierre-Julien, measuring approximately 25 meters in length, is engineered for harbor assistance, escort duties, and coastal towing operations, combining compact dimensions with high bollard pull performance. Its hull form is optimized for stability and efficiency, while modern control systems allow precise handling in confined port environments, confirming its readiness for demanding maritime service. Ship and rig repair operations at Azimuth shipyards represent a comprehensive marine service capability, supporting commercial fleets and offshore energy assets across the Arabian Gulf. Located in Dammam, the yard handles projects ranging from routine vessel maintenance to complex offshore rig refurbishment. Dry docking procedures allow full access to hull structures, propulsion systems, and underwater equipment, while specialized teams conduct steel renewal, mechanical overhauls, and coating applications under strict quality standards. Offshore rigs receive structural inspections, equipment servicing, and safety system upgrades to maintain operational readiness in harsh environments. Heavy lifting infrastructure, skilled workforce expertise, and integrated project management enable efficient turnaround schedules. Each completed project reflects technical precision, safety discipline, and the ability to restore critical maritime assets to reliable service. The assembly of the ABB Azipod propulsion unit represents one of the most advanced processes in modern marine engineering. As a gearless, steerable propulsion system with the electric motor housed inside an external pod, Azipod technology delivers 360-degree rotation, exceptional maneuverability, and up to 20% improved fuel efficiency compared with conventional shaft line configurations. Over 3 decades, it has transformed vessel performance standards across global shipping. Production begins with precision shrink fitting of the stator, where controlled thermal expansion ensures a perfect interference fit within the motor housing. This is followed by detailed shaft line and thrust bearing assembly, forming the structural backbone responsible for transmitting propulsion forces and absorbing axial loads. Rotor installation requires micron-level alignment tolerances to maintain electromagnetic efficiency and mechanical stability under extreme operating conditions. Outfitting stages integrate cooling systems, sealing arrangements, lubrication circuits, and steering mechanisms within the pod structure. Engineers then conduct comprehensive electrical and mechanical testing, including vibration analysis, insulation verification, and rotational performance checks. The completed Azipod unit emerges as a fully integrated propulsion solution, combining power generation, steering, and thrust delivery into a single compact system. This engineering approach not only enhances vessel agility and operational reliability, but also supports reduced emissions, lower lifecycle costs, and improved sustainability across demanding maritime applications worldwide. Ship repair projects at Baku shipyard demonstrate the convergence of heavy industry capability and precision marine engineering required to maintain modern fleets. Located in Baku on the shores of the Caspian Sea, the facility plays a strategic role in supporting commercial shipping, offshore energy vessels, tankers, and specialized marine units operating throughout the region. Each repair campaign begins with carefully controlled dry docking procedures. Ballast adjustments, tug coordination, and docking alignment ensure the vessel is positioned accurately on keel blocks, allowing safe access to the hull and underwater systems. Once secured, inspection teams perform structural surveys, ultrasonic thickness measurements, and damage assessments to define the technical scope. Steel renewal operations may include plate replacement, reinforcement of frames, and restoration of load-bearing structures under Classification Society supervision. The process of bringing vessels into dry dock at Baku shipyard is a carefully orchestrated marine operation that combines navigation precision, ballast engineering, and coordinated teamwork. Approaching from the open waters of the Caspian Sea toward Baku, ships of many types, tankers, offshore support vessels, cargo carriers, and service craft, are guided by tugboats that control speed, heading, and lateral alignment to within tight tolerances. As the vessel enters the dock chamber, mooring crews secure heavy lines to stabilize position, while dock engineers verify alignment with pre-arranged keel blocks and side supports. Ballast systems play a critical role. Water levels inside the dock are precisely managed, so the ship remains afloat during positioning, but settles evenly once contact with the blocks begins. Communication between tugmasters, dock control, and onboard crew remains constant to prevent structural stress or misalignment. When positioning is confirmed, the dock gates close and powerful pumps begin removing water. Gradually, the hull emerges, revealing propellers, rudders, thrusters, and underwater structures. The moment when thousands of tons of steel transition from floating to fully supported on blocks represents the peak of technical accuracy. What follows is a stable, secure platform ready for inspection and repair, marking the successful completion of one of the most critical phases in shipyard operations. The VETH Integrated L-Drive, developed by VETH Propulsion, represents a breakthrough in compact marine propulsion engineering. Recognized as one of the world's most space-efficient electric drive systems, the design integrates the electric motor, vertical shaft, and gearbox into a single streamlined unit. This configuration minimizes installation footprint while maximizing efficiency, making it suitable for a wide range of vessels, from luxury superyachts to demanding commercial workboats. A key advantage lies in its flexible installation capability, allowing shipbuilders to optimize internal vessel layouts without sacrificing propulsion performance. The L-Drive delivers smooth torque transmission, reduced vibration levels, and lower acoustic signatures, which are particularly valuable for passenger comfort and environmentally sensitive operations. Advanced control electronics further enhance maneuverability and responsiveness, supporting precise vessel handling in confined waters. By combining compact architecture with high power density, the VETH integrated L drive enables improved energy efficiency, reduced maintenance requirements, and future readiness for hybrid or fully electric vessel concepts across modern maritime applications. On a drillship, running risers and installing the diverter system represent a critical transition from open water to controlled well operations. The sequence begins with heavy hoisting operations, where riser joints are lifted from storage and positioned vertically using the vessel's derrick and handling equipment. The telescopic joint, designed to absorb vertical vessel motion, is then prepared and carefully run into position, ensuring proper alignment with the marine riser string. As additional riser sections are deployed, crews install high-strength riser bolts at each flange connection, creating a pressure-tight structural column extending from the rig to the subsea wellhead. Precision torque control and inspection are essential, as these connections must withstand dynamic loads from currents, waves, and drilling forces. In parallel, the diverter system is transferred from storage onto the catwalk and lifted to the rig floor. Once positioned, it is run into place and integrated with the upper riser assembly, providing a critical safety barrier to redirect unexpected shallow gas flows away from personnel and equipment. Handling operations continue with laying off buoyancy joints and repositioning the telescopic joint as required for configuration adjustments. Every movement demands coordination between crane operators, rig floor crews, and control systems, ensuring the risks. A complex offshore crane replacement campaign was executed on the Muluk platform. The modernization scope centered on replacing legacy lifting assets with a new generation Liebherr offshore crane RL 1500, while upgrading an existing Bow series crane with the same advanced control architecture. Execution required the installation of a temporary support crane, specifically a Liebherr 230 8/16 Latronic tower crane, positioned using engineered load distribution points to accommodate offshore structural constraints. Deconstruction of the existing Liebherr offshore crane Boss 65 850ths involved segmented dismantling under strict weight and stability limitations, with components transferred via a specially designed offshore transport frame to ensure safe handling in harsh marine conditions. A defining engineering feature of the project was the deployment of a unique Liebherr sliding system, enabling heavy crane modules to be maneuvered across the platform deck without extensive structural modification. This minimized downtime and reduced offshore risk exposure. Installation of the new RL 1500 crane followed precision alignment procedures, mechanical integration and commissioning of electronic control systems, including synchronization with platform power and safety networks. The project represents a significant lifecycle extension initiative, improving lifting capacity, operational reliability, and digital control capability, while maintaining continuous production readiness in one of the world's most demanding offshore environments. Transpooling of a 16-inch, 4.8-kilometer flexible flowline was executed at Khalid Port in the United Arab Emirates using the DP2 Special Service Utility and Construction Vessel Millennium 3. The operation involved controlled tension management, synchronized reel drive systems, and precise lay pattern monitoring to prevent torsion and ovalization. Engineers supervised load distribution across spooling drums while maintaining minimum bend radius compliance. Real-time instrumentation verified line integrity, ensuring the asset remained installation ready for offshore deployment following successful completion of the transfer campaign overall. The FPSO Senangol Kenguela departed the Daewoo Shipbuilding and Marine Engineering Yard after completion of integration, commissioning, and acceptance trials. Designed for deep-water Angolan fields, the unit features crude processing modules, gas handling systems, large-capacity storage tanks, and tandem offloading capability. Once on station, it will operate as a floating production hub, enabling subsea tiebacks while maintaining continuous export through shuttle tankers under demanding offshore conditions. A quick overview of a recent offshore conductor installation campaign in Brazil highlights the precision required during early, well construction phases. The operation involved lifting and positioning large-diameter conductors from a jackup or heavy-lift vessel, followed by controlled driving into the seabed using hydraulic hammers. Engineers monitored penetration depth, verticality, and soil resistance in real time to ensure structural integrity. Accurate conductor placement establishes the foundation for subsequent drilling operations, providing wellhead stability, load transfer capacity, and long-term protection against environmental and operational stresses in deep-water conditions. At Tenerife shipyards, daily operations reflect the scale and discipline of a modern offshore fabrication yard. Expansive quays, heavy-lift cranes, and specialized work zones support simultaneous projects ranging from vessel repair to complex offshore structure integration, such as the ONS Stavigron modules. Steel arrives as raw plate and profiles, then moves through cutting, forming, welding, and assembly stations under strict quality control. Engineers oversee dimensional accuracy, load calculations, and certification compliance, while technicians execute precision welding and outfitting tasks. The yard's modular workflow allows large components to be pre-assembled, tested, and prepared for transport, minimizing offshore installation time. Logistics teams coordinate heavy transport, load-out operations, and sea fastening to ensure safe delivery. Continuous inspection, non-destructive testing, and commissioning activities confirm structural integrity before deployment. The environment combines industrial intensity with engineering precision, illustrating how shipyard infrastructure transforms complex designs into operational offshore assets ready for global energy projects. The ultra-deepwater drillship West Tellus, operated by Seadrill, stands as a prime example of seventh-generation offshore drilling engineering, built to perform in some of the most technically demanding environments on Earth. Designed for operations in water depths reaching approximately 12,000 feet and drilling depths up to 40,000 feet, the vessel combines advanced marine architecture with high-capacity drilling systems to support complex exploration and development campaigns. A key feature of West Tellus is its dynamic positioning system, which uses multiple thrusters and computerized control algorithms to maintain precise station without anchors. This capability is essential for deepwater fields, where seabed anchoring is impractical and positional accuracy directly affects drilling safety. The vessel's dual-activity derrick allows simultaneous operations, such as drilling and casing preparation, significantly reducing overall well construction time and improving operational efficiency. Automated pipe handling systems, high-load cranes, and advanced blowout preventer deployment equipment further enhance safety by minimizing manual intervention in hazardous areas. The onboard power generation plant supports energy-intensive drilling operations while maintaining redundancy for critical systems. Accommodation facilities are designed for extended offshore campaigns, supporting large technical crews working around the clock. West Tellus has completed major contracts in regions including offshore Brazil, where deepwater reservoirs require both technological sophistication and operational endurance. Its performance history demonstrates the reliability of modern drillship design in high-pressure, high-temperature drilling environments. Overall, the vessel represents a convergence of naval engineering, automation, and offshore energy technology. By combining precision control, high drilling capacity, and operational flexibility, West Tellus continues to play a vital role in accessing hydrocarbon resources located beneath kilometers of ocean water and subsea rock formations. Precision, timing, and coordination define the moment when heavy casing transitions from rig floor to wellbore. During operations with the Doyon Drilling 16C crew, the Volant running tool system enables controlled casing deployment while maintaining alignment and rotational stability. The tool interfaces directly with the top drive, allowing simultaneous rotation and circulation to reduce friction and prevent sticking as the casing string advances into the well. Crew members monitor torque, weight, and fluid returns continuously, ensuring parameters remain within safe operational limits. The Volant system's hydraulic control improves connection efficiency and minimizes manual handling risks, enhancing both safety and productivity. The result is a streamlined casing operation where engineered equipment and experienced personnel work together to secure structural integrity deep below the surface. The Prelude FLNG, developed by Shell, marked a historic milestone as it departed Samsung Heavy Industries in Gyeonggi, South Korea, for its 800-kilometer journey to Australia. Measuring approximately 488 meters in length and 74 meters in width, with a fully loaded displacement exceeding 600,000 tons, Prelude is the largest floating offshore facility ever constructed. Designed to operate for 25 years without dry docking, it can produce around 3.6 million tons of LNG annually, along with condensate and LPG. After offshore hookup and commissioning, the facility will extract and liquefy natural gas directly at sea, redefining offshore energy production efficiency. Life aboard the ultra-deepwater drillship ENSCO DS-5, operated by ENSCO, unfolds approximately 135 miles off the coast of Louisiana in the challenging waters of the Gulf of Mexico. Working in depths exceeding 100 feet of water, crews drill wells approaching 500 feet, with the total distance from rig to drill bit extending nearly 6 miles. Operations run continuously, 24 hours a day, supported by advanced automation and high-capacity drilling systems. Personnel rotations follow a structured schedule, 12-hour shifts for 21 consecutive days, followed by 21 days off, while helicopter transport connects workers to the offshore site. Daily tower meetings coordinate safety procedures, weather updates, and operational planning. The vessel functions like a self-contained offshore community, accommodating up to 200 people, including marine crew, drilling specialists, maintenance teams, and catering staff. Technically, the drillship measures about 750 feet in length and uses 7,000 horsepower thrusters, with dynamic positioning to maintain station directly above the well. A 200-foot derrick handles massive loads of drilling equipment, while automated pipe systems and remotely operated vehicles support safe and efficient subsea operations. The environment combines industrial scale, precision engineering, and strong teamwork, forming a unique lifestyle where offshore professionals operate at the frontier of global energy production. Tenerife Shipyard successfully executed a highly demanding FPSO mooring system retrofit associated with the colossal GTA FPSO unit. The project required extensive engineering coordination to upgrade critical mooring components while maintaining structural integrity and schedule efficiency. Work scopes included chain replacement, connection hardware renewal, fair-lead inspections, and reinforcement of load transfer interfaces designed to withstand extreme offshore environmental forces. The retrofit campaign combined heavy lifting operations, precision alignment, and subsea interface preparation, supported by specialized handling equipment and temporary support structures. Engineers conducted detailed structural assessments and fatigue evaluations to confirm compatibility between the upgraded mooring configuration and the FPSO hull. Tight tolerances were essential to ensure proper load distribution across multiple mooring lines once deployed offshore. A major challenge involved logistics and space constraints within the yard, requiring phased execution and advanced planning to maneuver oversized components safely. Quality control procedures included non-destructive testing, dimensional verification, and load testing simulations prior to final installation approval. Completion of the retrofit significantly enhances station-keeping reliability, operational safety, and long-term asset performance for the GTA development offshore West Africa. The successful delivery demonstrates the shipyard's capability to manage complex offshore energy infrastructure upgrades involving ultra-large floating production systems under technically demanding conditions. Against the harsh winds and steel-gray waters of the offshore frontier, a single launch captures years of engineering ambition. The premier oil catcher area development in the North Sea reaches a defining moment as the first subsea bundle enters the water, an achievement delivered by Subsea 7 after years of design, fabrication, and coordination. Inside a single pipe-in-pipe carrier, multiple lifelines converge. Production flow, gas lift, water injection, power, and fiber optic control, all governed by intelligent manifolds connected to the FPSO. The launch signals more than progress. It demonstrates a shift toward faster, more efficient offshore installation. By eliminating extensive trenching and reducing vessel requirements, bundle technology reshapes project economics. As towing preparations begin, another milestone approaches, confirming the scale and precision of modern subsea engineering. Lowering a 30-inch conductor pipe marks one of the most critical early milestones in well construction, establishing the structural foundation for all subsequent drilling operations. The massive conductor section is lifted into position using heavy rig handling systems, then carefully aligned over the well center before being driven or cemented into place. Precise control of verticality is essential, as the conductor stabilizes unconsolidated surface formations and prevents soil collapse around the wellbore. Crews continuously monitor load, penetration rate, and alignment while hydraulic or impact driving equipment advances the pipe to the required depth. Once secured, the conductor provides a stable guide for drilling assemblies, protects shallow groundwater zones, and ensures long-term well integrity. Nearly 400 meters beneath the shifting surface of the Norwegian Sea, precision engineering meets relentless ocean forces during the Naval subsea development. Operating from a rig managed by Transocean, crews reached a major milestone with the landing, locking, and testing of multiple 52-ton Christmas trees onto the seabed template. Installation demanded exact load control, as the massive structures were skidded beneath the moon pool and lowered through the turbulent splash zone using motion-compensated lifting systems capable of stabilizing heavy equipment despite wave-induced rig movement. Once positioned, remotely operated vehicles guided final alignment and connection to wellheads before pressure testing confirmed integrity. The operation marked a decisive transition from drilling toward completion, demonstrating how coordination, specialized equipment, and continuous communication enable complex subsea installations in one of offshore engineering's most demanding environments. Two vessels secured alongside one another during a fuel transfer operation represent a highly controlled maritime procedure known as ship-to-ship bunkering. In this scenario, the primary vessel remains moored to the quay, stabilized by shore mooring lines and fenders, while the secondary vessel positions itself parallel, carefully fastening mooring lines directly to the first ship. This configuration creates a floating transfer interface that allows fuel to be delivered without requiring both vessels to access the berth infrastructure. Precision dominates every phase of the operation. Tug assistance or thruster control is often used to achieve centimeter-level alignment, ensuring safe clearance between hulls. Pneumatic or foam fenders are deployed to absorb contact forces generated by wave motion, passing traffic, or wind loads. Once the vessels are secured, transfer hoses, typically reinforced composite or cryogenic rated depending on fuel type, are connected between manifold stations. Each connection undergoes leak testing and pressure verification before pumping commences. Fuel movement relies on calibrated transfer pumps, flow meters, and emergency shutdown systems integrated into both ships' control networks. Constant monitoring of pressure, temperature, and flow rate prevents overpressurization or vapor formation. Crew members maintain continuous radio communication, while spill containment equipment remains pre-positioned along deck perimeters to mitigate environmental risk. Structural loads also require attention. Mooring tensions shift as fuel weight redistributes between vessels, altering draft, trim, and stability characteristics. Officers continuously calculate hydrostatic changes to maintain safe freeboard and prevent excessive hull stress. Weather limits are strictly enforced. Operations may pause if wind speed, swell height, or current exceed predefined safety thresholds. Upon completion, lines are drained, hoses disconnected, and manifolds sealed with blind flanges. The receiving vessel performs quantity verification and documentation before the assisting vessel releases moorings and departs. This side-by-side transfer method provides logistical flexibility, reduces port congestion, and enables efficient fuel distribution within constrained harbor environments where berth availability or infrastructure capacity would otherwise limit maritime operations. Moving 88 tons of engineering excellence across continents demands precision, planning, and absolute control. In this project cargo operation, MSC safely transported a turret and 2 electro-hydraulic telescopic crane booms from Venice to Singapore, aboard the vessel MSC Ambra. The shipment, weighing 88 tons and reaching 25.5 meters, included transshipment at Gioia Tauro port before final barge delivery. The mission highlighted expertise in handling oversized, high-value cargo through synchronized logistics and meticulous risk management. Every phase was executed with strict safety protocols and continuous operational oversight. The HMM Universal Leader is a next-generation very large crude oil carrier engineered to move enormous volumes of crude oil across global energy routes with maximum efficiency. Constructed by Daewoo Shipbuilding and Marine Engineering for Hyundai Merchant Marine, the vessel represents a major step in fleet modernization, combining large cargo capacity with advanced environmental compliance systems. As the first in a series of 5 mega crude carriers ordered under HMM's long-term expansion strategy, the ship incorporates exhaust gas cleaning technology to meet sulfur emission regulations while optimizing propulsion performance and fuel economy. Designed for both spot market operations and long-term charter deployment, it reflects the evolving demands of global oil transportation logistics. Beyond its technical specifications, Universal Leader symbolizes a strategic investment in scale, efficiency, and sustainability within the tanker sector. Its immense hull dimensions, high deadweight capacity, and modern onboard systems position it among the new generation of ultra-efficient crude carriers shaping international maritime trade. The installation, commissioning, and testing of the 3,000 metric ton offshore mast crane aboard Bocalift 1 marked a major engineering achievement for Boskalis and crane manufacturer Huisman. Executed in China within just 27 days, well ahead of schedule, the project demonstrated exceptional planning, structural integration expertise, and commissioning efficiency under demanding technical conditions. Bocalift 1 itself represents a complex conversion project, transformed from a semi-submersible heavy-lift vessel into a fully self-propelled crane ship capable of executing large offshore installation campaigns. To accommodate the enormous lifting capacity, engineers first reinforced the vessel's structural framework, ensuring that load paths from the crane pedestal could be safely distributed through the hull. Precision alignment during pedestal installation was critical, as even minor deviations could affect crane performance under extreme loads. Mechanical integration included assembly of the mast sections, hoisting systems, winches, and slewing mechanisms, followed by hydraulic piping, electrical cabling, and advanced control system connections. Commissioning teams then performed calibration of load monitoring sensors, motion control systems, and safety interlocks to confirm operational accuracy. Functional testing simulated real offshore lifting scenarios, including dynamic load cases, emergency stops, and redundancy verification across critical systems. Equally important were vessel stability assessments, ensuring that the ship could maintain safe operational margins while lifting massive offshore components in varying sea states. These evaluations confirmed readiness for complex installation missions. With the crane fully operational, Bocalift 1 is now optimized for large-scale offshore energy projects, including installation of jackets, monopiles, and next-generation offshore wind turbines. The successful execution of this project highlights how advanced crane technology, naval engineering, and rapid project delivery can converge to expand heavy offshore construction capability on a global scale. At Germany, containerized cargo moves seamlessly between ocean vessels, inland barges, rail corridors, and road transport through synchronized scheduling platforms. Inland depots function as consolidation and distribution hubs, optimizing load efficiency and reducing transit time. Digital tracking systems monitor cargo position, environmental conditions, and handling milestones in real time, ensuring supply chain transparency. This coordinated transport architecture maximizes reliability, minimizes delays, and maintains cargo integrity from origin to final delivery across international logistics routes. Massive lock gates for the expanded Panama Canal arrive in a remarkable heavy lift operation, captured through stunning aerial views. Transported across oceans, these colossal steel structures mark a historic upgrade, enabling larger vessels to transit. Their delivery represents precision engineering, global logistics coordination, and a transformative milestone in maritime trade capacity. The tug Portobello, operated by SAM Towage Uruguay, delivers reliable and efficient harbor assistance services every day. Designed for strength and precision, Portobello supports vessel maneuvering, docking, and undocking operations in busy port environments. With a skilled crew and modern towing equipment, the tug ensures safe navigation and optimal control, even in challenging weather conditions. Committed to maritime safety and operational excellence, Portobello plays a vital role in maintaining smooth port logistics and protecting vessels, cargo, and infrastructure. On Saturday, the 12th of July, Bascalis successfully loaded the cruise ship Carnival Vista onto the heavy-lift vessel Boca Vanguard, creating a unique floating dry dock solution. As the world's largest heavy lift vessel, Boca Vanguard submerged its deck by filling ballast tanks, allowing the 325-meter ship to maneuver precisely into position. Once aligned, controlled deballasting lifted Carnival Vista completely out of the water. Inside the port environment, the vessel effectively functioned as a mobile dry dock, enabling maintenance without conventional shipyard infrastructure, demonstrating innovative offshore transport and engineering capability at extraordinary scale. On October 29, 2020, the EasyMax 2 vessel was successfully launched at Royal Eastern Sander, marking another milestone in efficient cargo vessel innovation. The launch process involved transferring the hull from the construction hull onto a slipway using hydraulic skidding systems, followed by controlled descent into the water with synchronized release mechanisms. Engineers monitored structural loads, alignment, and buoyancy response throughout the operation. Once afloat, the vessel underwent initial stability checks and mooring procedures, confirming readiness for outfitting and sea trials before entering commercial service. As the vessel Arklow Bay entered the water during launch at Ferris Smith Shipyard in Westerbrook, the sheer displacement created a dramatic surge, sending waves rushing over nearby roads and quay surfaces. Built for Arklow shipping, the ship's controlled slipway launch demonstrated the immense forces involved when thousands of tons meet the water simultaneously. Engineers had carefully calculated buoyancy, drag, and stopping distances, ensuring the spectacle remained safe while showcasing the raw power of large-scale shipbuilding operations. Imagine cruising through historic streets, then suddenly splashing straight into a river without changing vehicles. That's the magic of Hippotrip in Lisbon, an amphibious adventure that turns sightseeing into a mini expedition. Built with robust boat-grade engineering, the vehicle seamlessly shifts from road to water on the Tagus River, surprising passengers every time. With lively guides, panoramic views, and a dramatic water entry moment, the experience blends tourism with engineering curiosity, creating a fun and unforgettable way to explore Lisbon. Berg Propulsion Azimuth thrusters deliver full 360-degree vectoring thrust through a rotating propeller pod, enabling exceptional maneuverability and station-keeping accuracy. The system integrates advanced gear transmission, optimized hydrodynamic blade design, and intelligent control interfaces to maximize thrust efficiency while reducing fuel consumption and emissions. Suitable for offshore vessels, tugs, ferries, and dynamic positioning ships, these thrusters allow precise lateral movement, zero-radius turning, and stable positioning in demanding marine environments.